So, good morning. My name is Stefan Schmidt. Warm welcome from my side. I'm the Managing Director of the Open Hybrid Lab Factory in Wolfsburg, and it's an honor for me, it's a pleasure to have here this moderation on this session. The first session here of the LightCon conference, the first one, and our topic of the session is sustainable engineering and design. And we have got the first speaker is Mrs. Astrid Heckl, and from the Schaeffler Technology AG. She's team leader in materials and processes and has his background in material science. And yeah, I would like to hand over to you, and I wish everyone an interesting presentation.
Thank you very much, Mr. Schmidt. Welcome from my side. Hi, I'm Astrid, and I hope I can give you today a little bit of insight how we do some manufacturing innovations, how we light up manufacturing technologies, and also maybe an answer why the organizers of this conference are some very clever people. But let's see. Where do I have to click? Here we go. So as announced, I'm coming from the Schaeffler Technologies, and Schaeffler Technologies, for those who don't know the company, was founded in 1947, more than 75 years ago, and had a very strong background already in the 1950s to expand. So here you can see the numbers of the company. I only want to point out where we are spread out, which is more than 200 locations worldwide, in more than 50 countries, and another number, which is here, the patents. Schaeffler Technologies is a company which is quite innovative and technology-driven, and I also kind of like our motto, which is we pioneer motion. And when you see all these different fields of application where our products go to, you basically could say you will never have a single day in your life where you do not come across one of our products. Even if you go to the dentist around the corner, because little bearings are also in the dentist's toolings. So there are many, many fields of our products, very widespread, which makes it also very interesting to work in these fields. You can find us on the Hannover Messe, mainly on the industrial automation in Hall 6. Today, I will bring you up 3 different examples how we light up the manufacturing technologies. 2 of them are displayed here as well. The one is aerospace, and the other one is coming from the wind. And the third one is a kind of general one. Coming from Schaeffler to the department where I'm from, so this is called Advanced Manufacturing Technologies, and our focus here is to identify, but also to evaluate new technologies, and also to development of these technologies. And it can be illustrated here on the right-hand side on the so-called Technology Readiness Levels, established from NASA many years ago. So we are basically looking from an TRL-2, 3 at the beginning, where we find out some new ideas, some new innovations, and then going into some kind of proof of concepts, looking some economical but also technical feasibility, and end up, if this is worthwhile, to go deeper, up to really do the development for the first prototypes, and then afterwards we do have a parallel department which is mainly focused on the serial implementation. And at the beginning I said maybe also have an answer why I think these people from the organizational committee of the conference are quite clever. All the sessions here are organized in materials, process, and design. And examples. And this is what you can see here on the left-hand side. This is exactly the field where we are looking into, not separately, so not only material, not only the process or possibilities in design, always in combination. And I think these 3 are the main drivers to reduce also CO2 reduction, and especially in combination, they can really generate good new things. Coming to the first example, I think all of you know different additive manufacturing technologies. Our department is called Advanced Manufacturing Technologies. However, we also have a lot of additive technologies. One of them, widely spread everywhere, is the fused filament fabrication. You have some material which is placed as a filament. You have some process head, which is then printing the part, and then afterwards you have kind of component. When we started on that field, we had local printers, tried out something, and then we expanded that. We brought the printers into the different sites, which have been many, as you've seen at the beginning. Well, from first samples, you also have the thing of packaging everything, then you spread out, you have it locally. And then we said, okay, now we can produce locally, we can save a lot of logistics, we can save packaging material, we can save a lot of things. However, there is still the thing that packaging is also generated elsewhere. So we do have a lot of packaging waste, and so we had the vision to introduce circular economy for the technology fused filament fabrication by just using our packaging waste. And how can you do so? The process looks like that. You just collect the polymer waste. It's important that you have thermoplastics, that you can use the plastics. And so far, we focused on a collection in our sites for blister foils because they're very easily to identify as a thermoplastic material. Of course, there are some more, but for the beginning, this is easy to identify. Then we did the first example here to have a proof of concept if that could work. So we shredded the foils. There we had a lessons learned. It's not so easy to shredder blister foils because they're weak. So the lessons learned was to stiffen the material by having some pre-melting with hot air. But we generally can generate zero loss of material. Then you compound that, add some fillings, and you end up having that filament which can be used on the printer. That worked quite well, so we just recently had the first proof of concept done and printed with a FFF printing machine locally. Such a holder, that's just the first sample coming out. Card holder, as you maybe also know it from your company, where you can stick in your card. And now we're going, of course, the next steps forward. And we're doing that in collaboration with the department of Mr. Drummer in Erlangen. So now you could say, okay, well, that's circular economy, but is there any other benefit of that? And of course there is, because what you can see here is the waste which is generated only in Germany out of 2019 for the whole industry. And if you look into the industry, it's 12.3 tons of primary plastics has been used. And only the recycling quote out of that is less than 14. So there's a lot of potential to do anything better. And also what you can see here listed is the thermoplastics is a fairly high amount, so it's quite easy to have a first good step into. And we calculated what kind of waste is produced. So we have only with the blister foils in our production sites around 100 to 200 kilograms of blister foil waste every year. And we have, as you've seen at the beginning, more than 50 sites. So if I just calculate it by 50, that's a lot of waste which we can use. And that this is also economically and ecologically feasible can be listed here. So we first had the machines being placed locally. Now we collect the waste locally, and we can produce different kinds of parts in the future. That can be for production sites, some toolings, guide rails, whatever is necessary, and can be printed out of that foils. And that this is quite a large number. I tried to figure it out on the right-hand side below. If you only count like 200 grams such a part can weigh, of course it's just a rough estimation, you can fabricate out of your only blister foil weight 500 to 1,000 components every year per site. And this equals, if you calculate the price for such filaments, up to 2,000 or 4,000 euros. So it's quite worthwhile, and we're quite happy that we did the first proof of concept, which worked, and going now much deeper in that topic. Coming to the second example, as you've seen before, we have a lot of different branches where our products go to, and one of them is the aircraft applications. So we have bearings which go in such turbines. You can see here illustrated where the bearings are located in the turbine. And especially during takeoff, such bearings, or airplanes in general, have a lot of stress on all the components in the turbine. So the idea was, how could we do any improvements on that? And the idea was, if you look onto how to reduce such friction possibilities which occur during the stressing of the bearing, you can we came up with the idea to just simply cool the bearings down, that you reduce the temperature, you reduce the friction, and having so improvements which can be less use of lubrication, longer lifetime, but also having lower temperatures. Or on the other side, if you can keep the temperature same, you can increase the power densities and the engine speeds, basically. So how can you just do so? First of all, what you can see here, that's a typical bearing, cross-section of a bearing with an inner ring, the cage, and the ball bearing inside, and an outer ring. And what you can see here is there are some millings done to establish some cooling channels. And those cooling channels to be generated with conventional technologies means you have to halve the outer ring first, you have to mill that all, then you have to bring it together and have to have a two-ring assembly on top to be able to have such cooling channels established at all. So here we had a look into different process technologies and also designs, and came up here with the idea of having these channels done by additive manufacture. I'm hurry up. So here the advantage is you only have one ring. You can place the channels quite closer to the raceway, and you end up having 30% less material, which can be used afterwards. And every kind of material saving is some kind of CO2 saving at the end. And here you can also see comparison of the different process change. The upper one is for the additive route, and the other one would be for conventional technologies. You have here in the middle the different process steps to be able to install the channels at all. And the rest here beside the HIP process is the same. But also beside the 30% of material saving, you would have here a 60% of time saving for the process steps. And that this works is shown here. So you can see from the left-hand to the right-hand side of the pictures the temperature, which is erasing. And as a summary, for the material or the bearing done by additive manufacturing, you can reach up a 40-degree decrease in temperature, where just due to the channels, and also the position of the channels, which is then much closer to the raceway. And also you have here maybe just a look on the right lower corner. Then you can save some oil, which is of course CO2 reduction. You have power loss reduction, and the temperature reduction in operating time. And then a quick look into our third example. This is a little bit more ripened in progress, coming from the wind turbines. So here you have such plain bearings which sit inside such a gear stage in the gearbox. And state of the art here is that you use some bronze, so the golden part on the pin is the bronze, which is usually casted. And by casting such a bush, you need a lot of different sizes for the geometries. You only have a press fit of the material. You need a lot of material usage, so it's 30.6 kilogram, which we need with the traditional route. And there's a lot of process steps, only some limited ones displayed here. Now we changed, or we're going to change the technology and going into some laser-cladded process route. There, of course, you have the advantage that you're totally flexible for the geometry. You have a very strong conjunction in between the materials, and you have less material usage, which is only 2.9 kilograms. And here you can save up to 95% of CO2 compared to this process. And also a process steps reduction, so there are several other advantages in saving some process time and also cost in there. And this conference is called Circular Economy, so I tried to also point out how we look deeper into that. So we have established already the process for development. You go typically from studies to material testing to the sampling and the test rigs, and some calculations, always assisted by process simulations, which is very, very helpful to gain some new ideas and some new insight how the interaction in between all the parameters and the material is. And then once this is established, and this is where we are right now, we again think of how to make it even better with circular economy and how to even more increase the CO2 reduction. So what you basically have is you start off from the power raw material, then you have your process, and afterwards your component. And improvements by circular economy, the first two listed here, the one is coming from the powder material. So here we are talking about increasing the amount of secondary material which is used to produce the powder. This makes up to 15% of the CO2 reduction possible, even more if you can increase more, but this seems to be the limit at the moment. And for the process itself, you have some kind of overspray, and here we have now a new concept how to collect the overspray, how to rework the overspray powder, to really also bring it back into the process to really have ideally zero waste out of your powder. And this also makes up to at least 15%, up to 20%, where you can increase your CO2 footprint, which is pure circular economy of the powder which is used in the process. Of course, you can also have some look into the component, how when it's machined afterwards, if there are some possibilities. And for CO2 reductions, you have some further ones. For example, how with the parameters from the process, how you can further increase that or improve that. And also from the output, which is coming from the powder production. But as I said, main input is for those two, which is pure circular economy, and is now going into real development to bring it into serial production then afterwards. And then I hope I do not stress you totally with your time. I tried to do a little summary. For me, as I said, the material, process, and design are the three components which are the main driver to have these CO2 reductions. And considering them all three together, that makes really solutions which are beyond expectation. I tried to summarize that below for the three different examples I've brought up today. So you see that's always a combination out of those 3 bullet points. And last but not least, I'd like to thank you, would say we have with manufacturing technologies possible solutions to make our world even better. It's good today, but to make it even better, especially for CO2 reductions and circular economy. And I would like to thank you for your attention.
Thanks, Astrid, for this nice presentation and all these ideas and concepts. Do we have any questions in the audience? We have on the left, on the right side, microphone, so you're welcome to use it. So my first question here is, you have shown us a lot of ideas and concepts, and I think you have got more concepts in your suitcase. Do you have any systematic approach to elect this kind of ideas, to evaluate it, which one is best suitable for you? Or?
Yeah, we do have. Basically, we're coming from either ideas from Hannover Messe or anywhere else. We're coming from ideas from newspapers. We're coming from, which is a big part, things from where there's a pain, an issue from the production side, or also from the development from our business units. And then we generate a lot of ideas. All those ideas are evaluated first, basically prioritized, and then we step into first screening of that method. Who are players? How does it work? Is there some technical but also economical feasibility, but first on a piece of paper? And then once we evaluated that, then we go one step further and really do some proof of concepts with on the machine, either by ourselves or with partners, very often also with partners, to see a little bit more detail if that there's a technical feasibility, and also we're looking more detailed into the economical feasibility. And then if this is still positive, then we go further, always having in mind sustainability, having in mind CO2 footprint. A little bit later, maybe the circular economy. This is what we do when we're already one step further, where there's some additional potentials. But this is basically step by step, coming from a lot of ideas and narrowing them down, and until we've sorted out the best ideas, which we then follow up.
Okay, thanks for this answer. Last chance for a question. Otherwise, I would have also a second question about the bearings. Is there a possibility to look in the full cycle, the circular economy, to use a bearing a second time or something like that?
Yes, there
is.
Even
in aviation?
It's not out of the aerospace, which I've shown today, but we definitely have some repair and refurbishment in mind, where we try to just the part when it fails, where there's some problems, or also for certain maintenance steps, just to not throw it away, but to refurbish the whole part, that you just demount the part. Then you would just repair by, for example, reducing the height where you have cracks or whatever appeared, and then applying new material, which is then generated basically full new ring, so you can bring it fully back into the machinery, and you do not need to have a full new component. Okay. That's also what we do, yeah.
Thanks a lot.